Let us look at proposition number 8 of works of Archimedes, specifically from on conoids and spheroids. The proposition says, given an ellipse, a plane through one of its axes A prime and perpendicular to the plane of the ellipse, and a line CO drawn from C the center in the given plane through AA prime, but not perpendicular to A prime. It is possible to find a cone with vertex O such that the given ellipse is a section of it. Let's see what this statement means first. Given an ellipse with A prime as the major axis and BB prime as the minor axis and center at C in the plane perpendicular to the plane of the paper. Let there be a plane perpendicular to the ellipse through AA prime. This is the plane of the ellipse, and this is the plane perpendicular to the ellipse. Draw OC in the above plane such that OC is not perpendicular to A prime. So here OC is perpendicular to the plane of the ellipse passing through A prime, but it is not perpendicular to A prime. Produce OA prime to D such that OA is equal to OD. So let's produce OA prime and let's intersect this line in such a way that OA is equal to OD, and join AD and OE, and let's also join OA, and let's extend it. Later on anyhow we will require it. So here what have we achieved here? Remember, this OC was not perpendicular to AA prime. So by carrying out this construction, we have arrived at AD on which OE is perpendicular. Let's draw FG parallel to AD passing through C. Let there be a plane through AD perpendicular to the plane of the paper. So let's bring in that plane. Now here, conditionally we have to proceed. If BC square is equal to FC times CG, draw a circle with diameter AD. Or if BC square is not equal to FC times CG, an ellipse on AD has axis such that the other axis D is given by D square is to AD square is equal to CB square is to FC times CG. So here what is happening is, if BC is not the mean proportional between FC and CG, then we draw an ellipse. If it is the mean proportional, then we draw a circle. So let's proceed to draw the ellipse, because here I have kept it in such a way that BC square is not equal to FC times CG. So now what do? We arrive at the other axis using D square is to AD square is equal to CB square is to FC times CG. And let's say the other axis is UV. That is, UV is equal to D. Let's actually build the cone with vertex O, whose surface passes through this purple ellipse. And this we have seen in our previous proposition. So here what have we done is, we were given an ellipse with OC not perpendicular to the major axis, but at an angle. What we have done is, we have converted it in such a way that we have an ellipse on which we have OE as a perpendicular, which satisfies the requirement to arrive at a cone as per our previous proposition. So now we construct a circle so that on that circle, if we draw a cone to O, these two ellipses, any points on them will be on the surface of that cone. And because OE is perpendicular to AD, we can do it because we have seen it in our previous proposition. So we extend OE, we extend OV, we extend OU, and we take a point Z on the extended OE and draw a line UZ so that it intersects with OV, the extended line OV at W. So now this point Z has been taken in such a way that UZ times ZW is to OZ square is equal to DE square is to OE square. Now we take the plane through UW, and in this we draw a circle with UW as a diameter. Let P be any point on the given ellipse. Let's say this is the point P. Draw PN perpendicular to A prime. So PN is perpendicular to AA prime. Join ON and produce it to meet AD at M. And let's join OP and extend it. Through M, draw HK parallel to AA prime. Draw MQ perpendicular to HK in the plane of the ellipse on AD, meeting the ellipse or circle about AD in Q. Now we have set it up. Now let's take it step by step. If we take these two triangles, then the ratio QM square is to HM times MK. Now this can be written as QM square is to DM times MA times DM times AM is to HM times MK. So basically what we are doing is we are multiplying the antecedent and the consequent by the same magnitudes. QM square is to DM times MA. It's the same ratio as UV square is to AD square times, again this ratio will be equal to this ratio. So now we have UV square is to AD square. Remember UV is the minor axis of purple ellipse is to AD square. That is the major axis of the purple ellipse. FC times CG, FC times CG is to A prime C times AC. Now, UV square is to AD square is the same ratio as BC square is to FC times CG. So we substitute UV square is to AD square with BC square is to FC times CG. And we already have FC times CG is to A prime C times AC. So here FC times CG, here it is the antecedent and here it is the consequent. So they cancel out. And we are left with QM square is to HM times MK is equal to BC square is to A prime C times AC. BC square is to A prime C times AC. A prime C AC. So let me highlight that. Let's first get rid of this plane so that we can see much more clearly. So here you have PN square is to A prime n times NA, and they both are on the same semicircle, BC and PN. That means they will be in the same ratio. So BC square is to A prime C times AC, and PN square is to A prime N times NA will be the same ratio. So we take Pn square is to A prime N times NA. Now, alternately, we can say Qm square is to Pn square is equal to Hm times Mk is to A prime N times Na. Hm times Mk is to A prime N times Na. Hm times Mk is to A prime N is to Na. That ratio will be the same as the ratio OM square is to ON square. We can look at various triangles and prove that they are similar, and we will arrive at this conclusion, which means QM is to PN is equal to OM is to ON. That means PN is parallel to QM, because PN cuts this triangle OQM such that the sides are proportional, which means they are parallel, which means OPQ is a straight line. Now, P is a point on the given ellipse, is also on the surface of the ellipse on AD. So here, since OPQ is a straight line and P lies on the given ellipse, Q lies on the purple ellipse. So that means P is a point on the given ellipse is also on the surface of the ellipse on AD. Similarly, all points on the ellipse are also on the ellipse on AD. And finally, all the points on the ellipse on AD lies on the surface of the cone on the circle with diameter UW. This part is already proved in our previous proposition. So, given an ellipse on which we have a slanted OC, we can arrive at a cone of which this given ellipse is a section. So let me just do a little bit of animation so that you get an idea. So this is the cone that we have arrived at. Is the cone we can say elliptical cone, and you will notice that all the points, that point which is moving is visible. That means it is on the surface of the cone. And let's finally take, so again you will notice that point which is moving is always visible. That means it is on the surface of the cone. So that was proposition number 8 of works of Archimedes, specifically from on conoids and spheroids. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.